Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it.
This is chapter 1.4, which is on functions. Right? And before we talk about functions, let's talk about something called a relation. So a relation is a set of ordered pairs. Right? So for example, something like the set of the ordered pair -3, 5, 3, 9, 6, -2, -3, 16. All right? So that would be a relation. It is a set of ordered pairs. A function f from set A to set B is a relation that assigns to each element x in A exactly one element y in B. Alright? So a function f from set A to set B is a relation that assigns to each element x in A exactly one element y in B. So essentially what we're saying there is that the x values cannot be repeated, right? In here, set A is called the domain, and set B contains the range. All right. Notice I'm not saying that set B is the range; it just contains the range. We'll see what we mean by that in a second. So first, let's get some diagrams here. So first, let's say that we have this set A and set B, and in set A, let's say that we have these four elements. All right. And in set B, we've got these other four elements. All right. And let's say that this was paired this way. Let's make A go to 1, B also go to 1, C let's make it go to 2, and D let's make it go to 4. Okay. So these are my two sets. Perhaps I'll draw them this way. This is set A, and this is set B. Okay. Now in here, this is a function. All right. This is a function. It is a function because each element in A is assigned an element in B. All right, so everything's paired up somehow. It is okay for something like this to happen, right? It's okay for there to be two values in B that have, excuse me, two values in A that have been assigned the same value in B. That is fine. All right, there's no worry about that. The other thing to notice here is that these over here, 1, 2, and 4, those are the only ones that elements in A are being assigned to, right? So that set right there that I did in yellow, this is the range. Right, so the range would be the set of 1, 2, and 4. All right, that's that set. It is not the entire set B. All right, technically set B is called the codomain, but nobody ever really talks about that. All right, but here in yellow, that is the range. The values 1, 2, and 4 because those are the ones that are being hit by some element in A. All right. So this is a function. Um, Let's see an example of something that's not a function, right? So not a function. And we're going to start the same exact way. We're going to start by having some set A and some set B, in which they each have 4 elements. And set A is the letters, set B is the numbers. Okay. And again, here I'll talk about set A. Well, it'll be in blue, set B in green. Cool. Now, let's pair them up this way. A is still going there. Let's say B is paired up to 2 and to 3. Let's say that C is paired up to 4, right? And D is also paired up to 4, okay? Now this is not a function. This is not a function, and here's why. Here's the issue. The issue here is that this element right here is being paired up or is being sent to 2 different elements out in set B. So it's got 2 different values. However, something similar is happening over here, right? But this is okay. This is okay. There's no issue with multiple things being sent to the same value. The issue is when you've got one thing being sent to multiple values, all right? So that's why this is not a function, because B is assigned to 2 values, all right? So essentially, we've got a couple of different characteristics that we can talk about here to put it all together on how to tell if something is a function, if we have a function between 2 sets. So characteristics of a function from set A to set B, all right? The first characteristic is, well, each element in A must be matched with an element in B, all right? So in other words, the entire domain is being used. Some elements of B may not be matched with any element of A. In other words, it's okay for the entire codomain to not be used. All right, as we said, the range is just a subset of the codomain. 2 or more elements in A may be matched with the same element in B. All right, so we have multiple things in some set A going to the same element in B. But an element in A cannot be matched with multiple elements in B. All right, so essentially saying this over here is not okay. We cannot have one element being matched with multiple things on the other side. All right, so let's try to determine if something is a function. Determine if the relation is a function. Right? So let's say that we had the following relation. We had the set of -2, -1, 0, 1, 2, going to the set 3, 4, 5. All right. And let's say that we had something like this. Actually, let's fix that. All right. In here, the question is, well, is this relation a function? And the answer is no. How come? Well, where this fails to be a function is right there. All right. That's how that fails to be a function. Because we have two elements from our domain going to we have one element in our domain going to two different elements in our codomain. Notice in this case our codomain is also the range because the entire set is being used. Let's say that we have this. And that, right? So in here, is this a function? Well, the answer is yes. It's a function, all right? And the reason this is a function is because none of the x values were repeated. In general, we assume the x are in the domain and the y are in the codomain, all right? Otherwise, or the range. So that's essentially visually how to do it. You check for x values to not be repeated, all right? Now, in general, we don't really denote functions like that. We do y equals f of x, all right? In here, we're essentially saying that y is going to be a function, and if it is a function, we're calling it f. F here is the name of the function. X is the independent variable. And y is the dependent variable. All right. And again, here when we say something like f of x, what we're saying is what is the value of y when you plug in x. All right. That's essentially what that's saying when you say something like y equals f of x. So what would represent a function? So let's look at an equation. So which equation represents a function? So let's say I had something like x squared plus y squared is equal to 8. All right. If I solve for y here, right, because we want to have y equals f of x, we want to see if this y actually is a function of x. So if I solve for y here, well, what do I get? I end up with y squared is equal to 8 minus x squared. And if I take the square root of both sides, I end up with y is equal to plus or minus the square root of 8 minus x squared. Now in here, I'm going to tell you that this is not a function. How do I know that this is not a function? Well, think about this. Let's say, for example, that the x was equal to 1, all right? Well, let's make it simpler, 0. If I plug in x equals 0 into here, what do I get? I end up with just the square root of 8. So this tells me that y is equal to plus or minus the square root of 8. But plus or minus the square root of 8 is really saying that we've got two different values, radical 8 and negative radical 8. So we have the pairing of 0 radical 8 and 0 negative radical 8, which is bad. It's bad because we have the x being used up, that one x value being paired up with two different y values, all right? So we don't like that. So this is not a function. And again, it's because of this plus or minus, right? Anytime you have something like this, a plus or minus, when you solve for y, right away you're going to know that it is not a function. All right, it is not a function. So let's look at the next example. Let's say that I had something like y minus 36 minus 4x squared is equal to 0. So I want to see if this equation is a function, right? And well, how do we check? Well, we want to do is we want to solve for y. So if I solve for y here, I'm going to say, well, y is equal to, moving everything else to the other side, 4x squared plus 36. All right. Now this is a function. This is a function. How do I know? Because there's no value that I can plug into the x. There's no one value that when I plug it into the x, it would give me two different outputs, right? For example, if I plug in 1, right? If I let x equals 1, what do I get for y? Well, 4 times 1 is 4, right? Because 1 squared is 1. And then 4 plus 36 equals 40. So in this case, I only got one possible output, and there's no number that would be different for that, right? So in here, this is a function. All right, and the way we would denote it is we would say f of x is equal to 4x squared plus 36. So for this y equals f of x. It's a function. However, for example C, y is not equal to f of x. Y it's not a function, so we wouldn't be able to write it that way there. All right. Now, let's say I've been talking about plugging stuff in and all of these, right? We're not figured these out. Let's practice a little bit of that. So let's say that we had these are the instructions. Let f of x be equal to 10 minus 3x squared. All right. Evaluate the following. So let's say that I asked for f of 2. All right. What is this actually saying? This is saying, well, plug in 2 into the function f into the x values and see what you get. So I have 10 minus 3 times 2 squared. 2 squared is 4 times 3 is 12. 10 minus 12 is negative 2. Cool. Hopefully you remember how to do that. Let's say that I have f of negative 4. All right. So what does that give me? That gives me 10 minus 3 times negative 4 squared. Negative 4 squared is positive 16. 16 times 3 is 48. 10 minus 48 is negative 38. All right. So in here, my point is that, well, how do you evaluate these things? You replace the x, right? You replace the x value with whatever you had in parentheses. So if I had something like f of k, right? Well, what would that really be? That would be 10 minus 3k squared. And that's it. We're done, right? All I did was change the variable. It told me to plug in k, so I plugged in k. And the same idea, I'm going to talk a little bit on the side here. The same idea holds for whatever's inside there, like whatever's inside the parentheses. So if I had something like f of star, you would tell me that this is 10 minus 3 times star squared, right? If I said something like, what is f of happy face? You would say that's 10 minus 3 times happy face squared, right? If I said what's f of broccoli, you would say that's 10 minus 3 times broccoli squared. And just wanted to show you some of my amazing artistic skills. But anyway, with this, the point is that whatever's inside the parentheses replaces the x, right? Whatever's inside the parentheses replaces the x. So if I had something like f of x plus 1, right? Well, what would this be? Well, whatever's inside parentheses replaces the x. So I have 10 minus 3 times replacing this x with whatever's inside parentheses. X plus 1 squared. All right? This squared comes from this squared. But again, whatever was inside the parentheses, replace the x. And then from there, we could expand that, right? X plus 1 squared is x squared plus 2x plus 1. Distribute the negative 3. I mean, this is really just algebra, giving us negative 3x squared minus 6x plus 7. And I don't think I made a mistake there. Yeah, I don't see a mistake. All right, cool. So that's what you would get when you had f of x plus 1. Now, let's talk a little bit about something called a piecewise defined function. Piecewise defined function. There we go. Piecewise defined functions. And as the name would imply, they are functions which are defined piecewise. All right, and so let's see what we mean. So a function defined by two or more equations over a specified domain is called a piecewise defined function. Right? A function defined by two or more equations over a specified domain is called a piecewise defined function. So essentially, what I'm saying here is that we're splitting up the domain into two or more pieces. All right, that's why we have that piecewise defined thing. So let's see some examples. All right, so let's say that I have f of x being the piecewise defined function of 7, x plus 1, and x squared. And this is going to be, well, it's going to be 7 wherever x is less than negative 4. It's going to be x plus 1 wherever x is between negative 4 and 0. And it's going to be x squared wherever x is, let's do strictly greater than 0. Okay. So in here, well, what we're saying here is that for this piece of the domain, we've got this function. For this other piece of the domain, we've got this function. And for this last piece of the domain, we've got this function. All right. So that's why it's called the piecewise. All right. So now let's see. What does this look like? Well, what we're going to do is we're going to look at all three of these. All right. We're going to look at each of those separately. So I'm going to look at the equation of y equals 7. Y equals 7 is this horizontal line, right, at 7. Let's look at y equals x plus 1. Y equals x plus 1 is this line going this way, right? It crosses at negative 1 and at 1. I found that out by looking for the intercepts, right? And then we're going to look at y equals x squared, which is just simply a parabola centered at 0, right? That's not quadratic. So in here, when we go to look for our piecewise defined function to go to graph it, what we're essentially going to do is take the pieces that we care about in each of these. So for example, in the first one, we care about everything that's less than negative 4. So if here's negative 4, we care about everything that way, right? But not including that negative 4. So at negative 4, we're not going to take that point. For x plus 1, we care about the stuff going from negative 4 all the way up to 0, including negative 4, but not including 0. So let's say that here is negative 4. We care about this, including negative 4, and up until this piece, but we're not including what happens at 0. And then for x squared is everything that's greater than 0. So essentially this, but we don't care about what's happening at 0. So how do we put all that together? Well, let's look at it this way. If we have this, we're gonna say, well, we're cutting this piece put it over here. So let's say that here's -4. So we've got this line up to, well, not including, up to -4, but not including -4, right? So now, for the next piece, from -4 to 0, we're going to go ahead and copy this piece. And what did that do? That did something like this. It went from, if I plug in -4 into here, you see that we're at the height of -3, right? So this is at the height of -3. And maybe I should label these. This is at the height of 7. And this is at the height of -3. And we're going all the way up to 1. But at 1, it's an open circle. That's at the height of 1. So we got that part right there. And then for the rest of this, it is also open circle and then that, right? So there we go. This right here is f of x. All right, that piecewise function. So again, essentially what we did was we took each piece and graphed it separately and then put it all together. Now, do you have to do the middle step of graphing it separately? No, but I think it helps. All right, it helps visualize things. Let's do another one. Let's say that we had f of x being the set, well, the piecewise function of -3x plus 2, -3, and the square root of x. And we're going to do this as for x being less than 0, for x being equal to 0, and for x being greater than 0. All right? So again, we're going to look at each of these separately, and then we'll look at them all together so that we can figure out what this might look like. So this first one, y equals -3x plus 2. Well, what is that? That's a negative slope with a y-intercept of 2. So it looks something like this. Here's 2. The x-intercept is when y is equal to 0, which happens to be, in this case, 2/3. The next part is y equals -3 for x being equal to 0. So exactly at 0, we've got the point -3. All right. And then the last part, y equals the square root of x. Well, square root of x looks like this. But we're saying for everything that's greater than 0. Okay. So let's put this together, right? All these three together. What is that going to look like? So we said that we're going to take -3x plus 2 for the values that are less than 0. All right, for the values where x is less than 0. So we're going to say it's going to look something like this. Oh, that's awful. There we go. All right, I'm just copying this piece right here, not including what's happening at 0. The next part is y equals -3, where x is equal to 0. So there it is. This was at the height of 2. This is going to be at the height of -3. It's not drawn to scale. And then for everything after 0, it's just the square root of x. So for everything after 0, not including 0, it's just x. I mean, it's just square root of x. So that's what we have there. All right, so that's piecewise functions overall. Now let's look at the absolute value function. All right, so let's say that I have the absolute value of x. The absolute value of x is actually a piecewise function where we're saying it's just x for all the values that are greater than or equal to 0, and it's the negative of it, right? The negative of it when x is less than 0. All right, think about how the absolute value works. If I plugged in -3 and I said take the absolute value, well, the absolute value of -3 is +3. Arithmetically speaking, it's the same as multiplying by a -1 in front of it, right? So that's what this is doing. It's taking all the negative values, becoming positive. So graphically speaking, what does that really mean? Well, we can think of it this way. We've got, it's just x, right? It's just x. I can go ahead and graph just x, right? This is y equals x. And perhaps I'll do this in a different color in a second. But because we want it to be the absolute value, that means that we want all this part that's being negated, we want all of that to be, that all this part that's being negative, we want it all to be positive. And how do we do it? By negating. By negating a negative, it becomes a positive, right? So what we're going to do here is we're going to say, well, this piece right here, it's no longer going to look like that. It's going to look like, well, this positive part was there. So all this piece, this entire piece that was down here, now it's going to be up here. All right. So all of this gone. Now, that is simply just the absolute value of x. But how do we graph something that is a little bit more complicated than this? So let's say that we have the absolute value. So let's say that h of x was the absolute value of 2x minus 4. All right. So here's how we're going to graph this. We're going to say first step 1. We're going to say find the x-intercepts. All right. And the x-intercepts again is when y is equal to 0. All right. So how do we do that? Well, set this equal to 0. So we have 2x minus 4. Absolute value is equal to 0. Technically here, this gives me two equations, but they're the same. So it's just 2x minus 4 is equal to 0. So that x is equal to 2. And again, technically, the other equation that this would have given me would have been 2x minus 4 is equal to negative 0. But negative 0, that doesn't make sense. So we just resort to the same equation. All right. So, all right, so the x-intercept is 2. Next thing, the second step is to test around it. Test around intercept. Around. My spelling is not the greatest. So what do we mean by that? Well, we want to see where the function is being, where the function values are negative, right? So that like we can manipulate it. So what we mean is, well, let's say that here in the number line we've got 2. We can test something like to the right of it, like 3, and something to the left of it, like 0. In general, whenever you're testing values, 0, 1, and negative 1 are the easiest in that order. All right, so when we plug in 0, what do we get for the y value? All right, what we get for the function? We plug in 0. 2 times 0 is 2, 2 minus 4. Oh, we're going to plug it into just without the absolute value, right? Just in here. So 2 times 0 is 0 minus 4 is negative 4, so I get negative 4. When I plug in 3, 2 times 3 is 6 minus 4 is 2. Notice that this value is positive while this one's negative. The negative side is what needs to be negated. All right, so that's the part that we're going to be negating. All right, what does that mean? So our function h of x, which again was the absolute value of 2x minus 4, we're going to rewrite this as a piecewise function. And we're going to say, well, it's going to be just 2x minus 4 whenever the input, whenever the x values were greater than or equal, when the output was greater than or equal to 0. And that was over here where we had the positive values. So where it is greater than or equal to 2. Because again, all the values that were greater than 2, they gave us a positive value. So there we go. And then we're going to say, well, for everything that's less than 2, we're just going to take this and negate it. So it's going to be the negative of 2x minus 4. All right. But if you really wanted to, you can write it as negative 2x plus 4. All right. Or 4 minus 2x. But there we go. We just rewrote that as a piecewise function. Let's do another one. let's say that I had f of x being equal to the absolute value of 7 plus 2x, right? So what were the steps? Again, first was find the intercept. So the x-intercept is when y is equal to 0, and because we're setting it to 0, again, we just end up with one equation. So we end up with x equals -7/2, right? Subtract 7, divide by 2. Then the next thing I'm going to do is we're going to test around -7/2. So let's see. I'm testing around -7/2. To the right of it, there we go. I could test 0. To the left of it, well, -7/2 is -3.5. So I'm going to check -4, and I'm going to see what's happening to the y value, right? Where here, this is 7 plus 2x is the y value. So let's plug in 0. 7 plus 2x, well, 7 plus 2 times 0 is 7, which is a positive value. When we plug in -4, 2 times -4 is -8. 7 plus -8 is -1, so that's a negative value. So in here, all the values to the left of -7/2 are what needs to be negated, okay? So what we're going to say is, well, graphically speaking, this again would have been, well, 7 plus 2x. It would have been something like this. No, that's not true. There we go, way better. Because the x-intercept is at -7/2. So here at -7/2, we've got our x-intercept and everything over here. And over here, this was originally down here. It became up there. All right. Now, as a piecewise function, how is that written? Okay, well, f of x, and let's go back to writing in white. F of x is going to be what was the absolute value of 7 plus 2x, which is, well, the split of point is at x-intercept, so it's going to be, we're going to look at what happens above, where the x value is being -7/2, or where they're, yeah, to the right of it, and then to the left of it, -7/2. And we said that to the right of it, it's the positive values already, so we're going to leave those as they were, 7 plus 2x, all right, without changing anything. But to the left of it, that's what's being negated, all right? So that's the part that that you put a negative in front of. And that is absolute value functions overall. Now, how do we evaluate these? All right, how do we evaluate these? Well, let's look at an example. Let's say I probably should have lettered some of these examples just for future reference. So I'm gonna letter them right now. So it's I, J, K, L. Yeah. Oh, hold on. M. I think that's all of them. Okay. All right. So example N. Evaluate for f of x being x squared plus 1, for x being less than 0, and actually let's make this for x being less than 3, and x squared minus 1, or just x minus 1. X minus 1 for x being greater than or equal to 3, right? So let's see what happens here. Let's say that I said evaluate f of 3. Let's start easy. F of 0. Let's evaluate f of 0. Well, where does 0 fit in? In which domain does it fit in? Is 0 less than 3 or greater than or equal to 3? Well, 0 is less than 3, so we're going to use the definition up here, which was x squared plus 1. So that's 0 squared plus 1, which is 1. Cool. If I said f of 5, well, what's that going to be? Is 5 less than 3, or is 5 greater than or equal to 3? Well, 5 is greater than or equal to 3, so we say 5 minus 1, which is 4. And if we said f of 3, well, 3 is part of both of these, right? But if I say, well, is 3 less than 3? No, 3 is not less than 3. Is 3 greater than or equal to 3? Well, yes, because of the or equal to. So it needs to be plugged into this bottom part. So we have 3 minus 1, which is just 2. All right. So when you evaluate these piecewise defined functions, what you need to do is look at which piece of the domain should you be working in. All right. Now, let's since we're speaking about domains, let's talk about domain of a function, how to find it. So, unless otherwise specified, the domain of, or the implied domain, I should be saying, the implied domain of a function is the set of all real numbers or real number inputs that result in real number outputs. All right, unless otherwise specified, the implied domain of a function is a set of all real number inputs that result in a real number output. So let's see what we mean by that. Where was I at? N. So O. And here the instructions are find the domain. Let's shift that down. There we go. All right, so let's say that I have f of x being the square root of x plus 7. All right, so one thing that we know about square roots is that you're not allowed to have a negative value, all right, inside of it. So when we say what is the domain of a square root function, we're saying, well, what are the numbers that you are allowed to plug in, all right? And in here, if you recall, we're not allowed to have negatives in here, but we are allowed to have 0, and we're allowed to have positive numbers. So inside here, what we're saying is the domain is going to be where the inside, that x plus 7, is greater than or equal to 0. In other words, x being greater than or equal to negative 7, right? And that would be the domain. There's different ways to write this, all right? If you write it in set notation, set builder notation, it would be, I'll write it over here. The domain is the set of all x greater than or equal to, of all x, such that x is greater than or equal to negative 7. I would not worry about writing things in that kind of method. I would just say this right here, x is greater than or equal to negative 7. Or you can put it in interval notation, going from negative 7 to infinity. Yeah, that's the domain. All right. Either of these two are my preferred versions. Don't worry too much about that other one. Let's do another one. So that's O. P. Let's say that we have g of x being equal to 1 over 3 minus x. All right, now in here, we've got a fraction. And what are we not allowed to have in fractions? Well, we're not allowed to have zeros in the denominator of a fraction because then we would be dividing by 0. So I'm going to say, well, in here, what are we not allowed? All right, is 3 minus x cannot be equal to 0. Right? So that tells me that, well, 3 cannot be equal to x. Right? Normally we would write that as x cannot be equal to 3. And that would be our domain. In interval notation, it would be the set from negative infinity all the way up until 3, union 3 to infinity. But notice I didn't include infinity in either one of those. I mean, I didn't include, well, that was true, but I didn't include 3 in either one of those. So that would be that. In set builder notation, it would be the domain is a set of all x such that x is not equal to 3. Really, what I should be saying here is the set of all x in the reals such that x is not equal to 3. But again, I'm not going to be too worried about that notation. I'm more worried about you getting this notation over here. All right, so there's another one. So that's P. Let's say that I had something like f of x being equal to 1 over the square root of 9 minus 4x. All right. So in here, well, we've got a fraction, but we also have a square root. So what do we have? Well, for the domain, since we have a fraction, the denominator, so the square root of 9 minus 4x, cannot be equal to 0. But we also have a square root thing. So in here, that inside 9 minus 4x must be greater than or equal to 0. So these must both be true. There we go. These must both be true. I don't know why that's so difficult to say. So both of these statements must be true for the domain. So it has to not be equal to 0, and it has to be greater than or equal to 0. Well, that's just simply just saying that it's strictly greater than 0. Solving for x here, well, move the 9 over, so negative 4x is greater than 9. Divide by negative 4. 9 divided by negative 4 is negative 9/4, but because I'm dividing by a negative, that inequality symbol changes. So here, that's my domain. All right, that x is less than negative 9/4. In interval notation, that would say from negative infinity to negative 9/4, not including negative 9/4. All right, and again, in set builder notation, the domain would be the set of all x in the real value numbers such that x is less than negative 9/4. Cool. Let's do one more. R. Let's say that I had some function g of x and that was 1 over x squared minus 7x plus 10, right? And here, well, we've got a fraction. And what do we know about fractions? The denominator cannot be equal to 0, so we have x squared minus 7x plus 10 cannot be equal to 0. That's our domain, right? And in here, well, we can factor this. This is x, not plus 5, x minus 5 times x minus 2, right? Because negative 5 times negative 2 is positive 10, and negative 5 plus negative 2 is negative 7, so that cannot be equal to 0. So I get that x can't be 5, and x cannot be 2, right? So you could just simply say that that's the domain. X can't be 5 or 2. In set builder notation, you would say the domain is the set of all x in the real numbers such that x is not equal to 5 and x is not equal to 2. All right. In interval notation, well, what would this be? This would be from negative infinity up until 2, union 2 to 5, union 5 to infinity. All right. These are, it might have been helpful to look at this on a number line to see which values we care about. We care about everything except 2 and 5, right? So that's how I came up with that interval notation. All right, now, one last thing that I want to talk about. All right, and this will be the last thing for this section. And it is called the difference quotient, right? Difference quotient is something that you've probably seen already. It is given by the following. So first, let me tell you actually what it is graphically. If I have a curve, right? So some curve, and I've got a line going through that curve. This yellow line is called a secant line. All right, and on this secant line, let's say that they intersect each other there at some x value, and that over here, after some distance h, well, this value will be x plus h, right? The difference quotient is going to be the following. So f of x, well, actually, let's do the following. Let's look at the slope of this line. All right, so I'm going to call the slope m. And well, m is given by y sub 2 minus y sub 1 over x sub 2 minus x sub 1, right? But instead of calling this y, if I'm calling it f of x, then this is going to be, well, x sub 2, this is the sub 2, these are the sub 1s. So I'm going to have the x values are x plus h. Perhaps I'll write here what the coordinates are. This coordinate is x comma f of x. That's supposed to be a parenthesis. And this right here is x plus h comma f of x plus h. All right. So in here, y sub 2 minus y sub 1, well, it's going to be this value up here minus this value right here. So that's f of x plus h minus f of x. And let's change the color of all of that back to yellow. And at the bottom, I'm just going to have x sub 2 is x plus h minus x, which gives me our difference quotient, x plus h minus f of x, all of this over h. And this is only true as long as h is not equal to 0. All right. So in here, the difference quotient is just the slope of the secant line of a curve. All right. That is just the slope of a secant line. Now, let's see how to find it. All right. What letter was I at? R. So S. So in here, the instructions are find the difference quotient for the following. All right, and we're going to say we've got f of x is equal to x squared plus 2x minus 3. All right, so we want to find the difference quotient for that. So here's what we do. First, let's write down what the difference quotient was. All right, anytime you need to memorize some sort of formula, write down the formula. So it's f of x plus h minus f of x, all of it over h. Which means what? Well, I need to plug in x plus h. Remember when we were plugging in the star, the happy face, the broccoli? Well, what we did was whatever's inside the parentheses replaces the x. So what's inside parentheses? X plus h replaces this x. So x plus h squared plus 2 times x plus h minus 3. All right, that right there is f of x plus h minus f of x. Well, f of x is just x squared plus 2x minus 3. And we have all of that over h. The next thing we want to do is we want to expand as much as possible. So let's go ahead and expand here. In here, this x plus h squared, this is just x squared plus 2xh plus h squared. Distribute this 2 plus 2x plus 2h minus 3. Distribute this negative, minus x squared minus 2x plus 3, and all of that over h. At this point, if you did it correctly, and this is a good way to check that you're doing it correctly, anything on the numerator that doesn't have an x that doesn't have an h should cancel out. All right, if it doesn't have an h, it should cancel out. So x squared with minus x squared cancel out. 2x with negative 2x cancel out. Negative 3 with positive 3 cancel out. And the only stuff we're left with, it all has an h. So we have 2xh plus h squared plus 2h, and all of that over h. Now, because everything on the numerator has an h, you can factor out 1h. And I'm left with 2x plus h plus 2, and all of this over h. And now, there we're done. We just cancel out those h's. So we're left 2x plus h plus 2. All right. With the difference quotient problems, what we really want to do is get rid of that h in the denominator. All right. Let's do another one. Let's say that I had something like f of x is equal to negative 1 over x. All right. And again, let's find the difference quotient. So I'm going to start by writing down the difference quotient, which again was f of x plus h minus f of x all over h. And what does that give me? Well, I'm just replacing the x with x plus h. So I have a negative of 1 over x plus h minus negative 1 over x, right? And then all of that over h. All right. At this point, one thing that you'll notice here is that we have fractions on top of a fraction. All right, so we have fractions on the numerator. We don't like that. We don't like that only because it can get confusing. So what I'm going to do here is, first I'm going to remind you of this rule. If I have a over b, that's the same thing as saying 1 over b times a, right? It's the same exact thing. Think about it this way. Think about it going this way. 1 times a is a, and then the b times 1 is b, right? So I'm going to use that idea to rewrite this. This bottom, this 1 over b, is going to be just 1 over h, and that's an h, times the numerator. And the numerator is negative 1 over x plus h. Minus negative means plus, so plus 1 over x. All right. I highly recommend you do that whenever you're working with fractions in the difference quotient, just because it makes it a little bit cleaner. Now, the next thing we need to do is, well, I said that the main point of the difference quotient problems is to get rid of that h on the bottom. So let's see how we can do that. We haven't gotten rid of that h. That h is still there. So what can we do? Well, in here, in the parentheses, we combine like terms, right? But there's not really anything to combine. They're just fractions. So how do we combine fractions? Excuse me. How do we combine fractions? Well, we have to come up with a common denominator, right? A common mistake here is to think that the common denominator is x plus h. That's not the common denominator. Let's think about it. So if I had something like 1 over 3 and 1 over 5, well, the common denominator, that's its common denominator, would be 15, right? It wouldn't be 5, because think about this. 5 is the same as saying 3 plus 2. You wouldn't say that the common denominator is 3 plus 2, even though there's a 3 and a 3 there, right? You would say it's the product of those two. So similarly here, the common denominator is the product of those two. So we're going to have x plus h, and then times x. And then, well, when we have a common denominator, we must change the numerators. This one, to go from x plus h to this denominator, we have to multiply by x. So I'm going to multiply the numerator, which is negative 1, by x. So I have negative x. Plus, similarly, to go from x to this, I have to multiply by x plus h. So multiply this numerator by x plus h. At that point, you see that the negative x and the x cancel each other out. So I have 1 over h times h over x plus h times x. These h's cancel out, and I've got the final answer of 1 over x plus h times x. And now that we got rid of this original h that was on the bottom, we're done, right? I'll do one last one. This will be the last example here. Let's say that I have f of x is equal to the square root of x, and I want to do this, the difference quotient stuff. So what I'm going to say here is that, well, the difference quotient is f of x plus h minus f of x over h. In this case, that means the square root of x plus h minus the square root of x over h, right? Plug in x plus h into the x, square root of that. Now, what we need to do here is we need to manipulate this in some way so that we can actually get rid of that h on the bottom. And, well, there's two things you can always do to any math problem. One of them is add 0. The other one is multiply by 1, right? Adding 0 doesn't change anything. Multiplying by 1 changes nothing. So I'm going to multiply by 1 in this case. But we're going to be clever about it. And we're going to say that it is the square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. Before I tell you why we're doing it that way, notice that this fraction is just equal to 1, right? Same quantity on top as on bottom, so overall, that fraction is just equal to 1. Now, why did we choose that? Well, we chose that because we're multiplying by the conjugate of the numerator, all right? And I'll remind you real quick that if I have the product of conjugates, that gives me the difference of squares, all right? Normally, you might remember it as the difference of squares factors out to be the product of conjugates, but it's the same exact idea. And, well, what does that give me? Well, it's going to give me, well, a squared minus b squared, right? The product of conjugates. So, a, which was x plus h, the square squared minus the square root of x squared. The denominator, don't expand it, just multiply it out. Just put the multiplication. So h times the square root of x plus h plus the square root of x. In general, never expand the denominator. You get more information with it being factored, right? Now, what does it give us? Well, the square root of square cancels each other out. And down here, I still don't feel like rewriting that. There we go. That's what we get there. And from there, what you note is that the x's cancel each other out. And it's going to give me now that the numerator is just x. This means it's just h, right? And because it's just h, well, these two h's, they cancel each other out, giving me my final answer of 1 over all that. But we said the h canceled out. All right, so that would be my final answer there. We got rid of the h in the bottom that was originally there. All right. So that is the end of 1.4.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.